Okay, so we're going to be covering section 1.6 today, over nested quantifiers. And to get us started with what the idea is, we're going to look at an example here. So this is the kind of sentence that you have probably seen quite often in math. It says the sum of any two positive real numbers is positive. So I think that's pretty uncontroversial. If you add two positive things, you get another positive one. But what we want to do is think about this logically. We want to try to break it down using quantifiers and the kinds of propositional functions that we learned about in section 1.5. In order to think about our propositional function, though, we have to think about the number of variables that we're going to need. So how many different things is this sentence talking about? Well, it tells you. You don't have to guess. We're talking about two positive real numbers. So we actually have two variables this time, instead of a single variable like we had in our propositional functions in 1.5. So we have two variables, and we want to go ahead and give them names. Let's just call them x and y. And before we go on to rewriting this using symbols, let's go ahead and think about the propositional function that we're looking at as well. It has two variables in it, so when I write it, I need to make sure I have those two variables plugged in to my function, p of x, comma y. And this is going to be a statement, or a proposition really, about the two numbers x and y. And it says the sum of them is positive, so that's x plus y is positive, or you could even write that using an inequality. You could say x plus y is greater than 0. What's the domain of discourse for our propositional function?
All values of x and y.
All values of x and all values of y. Good. Let's see. I guess I need to come down here a little bit to write the domain of discourse. So we're thinking about pairs of numbers, pairs of real numbers. So that means our domain of discourse is not going to be just R, it's actually going to be R cross R. So this is, remember, the ordered pairs of real numbers that we learned about in the first section. The cross tells you the X, the multiplication symbol, tells you that you're looking at ordered pairs. Okay, so now we can write this symbolically because we know our propositional function. We know our variables are going to be called x and y. The final thing to do for our symbols is to consider how many quantifiers we're going to need. What do you think? Since we have two variables, how many quantifiers will we need?
Two.
Two. We're going to need one quantifier for each variable. Since this proposition is talking about any positive number, that means our quantifiers are both going to be the universal quantifiers, the upside down a's. So for all real numbers x and for all real numbers y, x plus y is positive, which we can just write using the propositional function p of xy, or we could actually write it using math symbols. Both of these would be fine if you want to think about it symbolically. This one uses a logic symbol for the propositional function. In here, we just use the math symbols. Okay, are there any questions right now? Okay, so let's give this idea a name, this idea of using multiple quantifiers. So here we're using two universal quantifiers. Expressions such as this are called nested quantifiers. So we're thinking about the right-hand quantifier coming after or being inside of the first quantifiers. Okay, so we have two different quantifiers, and we're going to, in this particular class, we're going to look at just combinations of two different, or two quantifiers. And if we have two quantifiers, A and E, there are going to be four possible ways to combine two of them. And I made a little table here for us to fill out.
Professor, can you go back up? I didn't get that last bit.
The blanks here.
Yeah, right.
Okay, so I can fill out this top row while he's writing. So the first possible way is the one that we've already seen, where you have two universal quantifiers, two A's. And what this one says is for all x and for all y. So let's just write that little phrase here. And then there would be something after that, if this was going to be, proper grammar. I'll just put some dots to represent the end of the sentence. You'll also often seen this just say, written or said out loud. It would be for all x and y instead of saying for all x and for all y. So often these extra words here, the second for all is left off. Okay, so that's the one that we've already seen. We can also have one universal quantifier and one existential quantifier. So this one would be for every x, there exists a y. Okay, that's how you would start whatever the rest of the sentence is. You can also have an existential quantifier and then a universal quantifier. So this one says there exists an x such that for every y, And then the fourth possible way to combine our quantifiers is with two existential quantifiers. And this one says there exists an x and there exists a y. Okay, so these are the four possible ways, and after this we're going to look at examples of each of them. I guess we've already seen an example of the first one, but we're going to look at examples for the others as well. Maybe I'll pause there for a second in case anyone's still writing.
I just arrived.
Okay. Yeah, thanks for letting me know. Okay, so let's look at some more examples of nested quantifiers. So what I want to do for each of these examples is think through how we would write it symbolically and determine the truth values of each of them. Let's see, and sorry about the background noise. There's a mower. Not sure if that comes through on the Zoom audio. So this example says, for all integers x, there exists an integer y such that x plus y is equal to 0. This example is like the upper right box. For every x, there exists a y. So that means we're going to be looking at a nested quantifier with a universal and then an existential. Okay, but we're getting a little bit ahead of ourselves. First of all, what is our domain of discourse? What kinds of things are we talking about?
Integers.
Integers, good. So both x and y are going to be integers. We're talking about pairs of integers. That means our domain of discourse is going to be z cross z. So this is the symbol for the set of integers. And this tells us that we're looking at ordered pairs of them. What is our propositional function? What are we saying about x and y?
That it's equal to 0?
Oh, right, x plus y is equal to 0. So if I give my propositional function the name p, where I'm plugging in my two integers, then this would be the equation, the mathematical proposition, x plus y is equal to 0. Good. So now we can put this together, these symbols, with the proposition to write it out symbolically. So we need a universal quantifier for x, for all integers x. And then we need an existential quantifier for y. There is an integer y. And then we can write our propositional function like this. Or if we want to keep the math symbols, we can actually write out the equation. So for all x, there exists a y such that x plus y is equal to 0, like this. Good. So these are the two ways that you could write it symbolically. Maybe there are others, but these are the two that we're going to talk about. Next, what's the truth value of this proposition? Is it true or false?
True.
It's true. Good. Let's spend just a second trying to justify that. So since you're saying this is true, that means that if I give you some integer x, you should be able to tell me an integer y where this equation is true, where x plus y is equal to 0. So if I gave you an x, what would your answer be for y? How would I pick y to make it
Negative x.
0? Minus x. Good. So let's just write out that in words. If y is equal to minus x, then x plus y is equal to x plus negative y. X plus negative x. We're just plugging in this value that we picked for y. And of course, this is going to be 0. Okay. Any questions over this first example? Or I guess this is actually the second example, counting the one with 2 universal quantifiers.
What is the truth value?
So are you asking what truth value means in general, or?
I guess so, yeah.
Okay, so a truth value for a proposition is either true or false.
So we're pretty much just saying that the whole statement is true.
Right, so if you said the truth value of your proposition is true, then what you're saying is that the proposition is true. Yeah,
That makes sense.
that's right. Okay, so let's switch the order. In this proposition, we had a universal and then an existential quantifier. Let's now do an existential and then a universal. So we're on the bottom left of that grid that we made on the first page. Since this one is written out in symbols, what we need to do is translate it back into words to make sure that we understand it. And we can just read off, or actually I think you could go back to the table and read off what this means, or you can work from scratch. You have an existential, so there exists. And we could also incorporate this other information. We're talking about pairs of integers. So x is an integer and y is an integer. So we could say there exists an integer x and y is also an integer, and this is a universal. So we could say such that for every integer y, and that takes care of the quantifiers and also the domain of discourse. Now we can just write the equation x plus y equals 0. So like I said, we were just switching up the quantifiers. This is exactly the same as the one before, except the order of the quantifiers. Okay, so read over that, make sure you understand what it's saying, and then let's see if we can determine the truth value. So is this true or false? There exists an integer x such that for every integer y, x plus y equals 0. What do you think? True or false?
False.
It's false. Good. That's correct. If this were true, if we were going to try to claim that this was true, we would have to come up with a number x that we can add to any other number and get 0. But of course, there is no such number. So this is false. Good. So the conclusion here, the important conclusion from this example, is that the order of the universal quantifiers, or the universal and the existential quantifiers, matters. Because when we changed the order in these two examples, so we went from this order to this order, the truth value changed. The first one was true, and the second one was false. So it definitely matters which order those quantifiers go in. Are there any questions over these examples?
So on number 2, I noticed on number 1 you had where you justified it. On number 2, is there like a way that you could show that it is false? Like I guess a way to justify that it is false.
Yes, yeah, you could justify it. The reason, maybe I won't write out all the details, but the reason why this would be false is that there's actually only one number that you can add to another number to get 0. And that was this one. It was the y equals minus x. So if we have different y values, we're going to have different x values as well. Does that make sense?
Yeah, that makes sense now.
Okay, good. Any other questions? Okay, so let's move on to the bottom right of our grid that we made earlier and put two existential quantifiers together. And this one is in symbolic form again, and we need to translate it into words. And just start reading left to right. This says there exists an x and there exists a y. And we can keep in mind our domain of discourse. Now we're talking about ordered pairs of positive integers. So z plus means the positive integers. And when you have this x, this multiplication sign in between them, it means ordered pairs. So ordered pairs of positive integers. So we should include that information in our translation, we should say x is a positive integer, is what I mean. So there exists a positive integer x. And there exists a positive integer y. Though this is the way that you would normally write that down in words. You wouldn't say there exists twice. You would just say there exists an x and a y. And now we have to translate this logical expression, this proposition, into words as well. So you can see we have three things in parentheses, and there's an and symbol in between each of them. So we can just write them out. X is greater than 1. Y is greater than 1. And x times y equals 10. Any questions about the translation here? Okay. So what about the truth value? Is this true or false?
True.
It's true, okay. So since we're claiming that this is true, that means we need to come up with values, since we're saying they exist. We need to actually come up with those values for x and y that have these three properties. So x needs to be greater than 1, y needs to be greater than 1, and their product needs to be 10. So what are those two values?
5 and
5
2.
and 2.
Good. Right, and it doesn't matter which one you pick for which variable. The order doesn't matter when you multiply. 2 times 5 is the same as 5 times 10. So what does this mean? Are there any mathematical terms related to this kind of thing? I'm being kind of vague on purpose here. What are we saying about the number 10? Maybe I'm being too vague. We're saying 10 is not prime.
Oh, not prime.
Because we can factor it into 2 times 10.
2 times 5.
Yes, excuse me, 2 times 5. Okay, so let's compare this first expression to this next one. So this one says there exists an x and there exists a y such that x is greater than 1, y is greater than 1, and x times y is equal to 5. Let me just write that down. And then you guys can think about the truth value while I'm writing.
So what's the domain of discourse for this?
It's the same. It's still the positive integers. So what do you think? Is this true or false?
False,
Right. Why is it false?
because 5 is a prime number.
Good. So because 5 is prime, we can't factor it into positive integers. Good. Okay. Any questions before we move on to the next topic?
Could you also just say false because 1 is not greater than 1?
I think what you're trying to say is that the only way to factor 5 is 5 times 1,
Yeah.
and 1 is not greater than 1. Yeah,
Yeah. Okay.
exactly. Okay, so the next topic is to think through how De Morgan's laws work for nested quantifiers. In section 1.5, we talked about how they worked with quantifiers, a single quantifier. Now let's think about what happens if there are two. So we're going to use what we learned before. Those were called the generalized De Morgan's laws, just to give them a name. Those were the laws that told us that when we put a negation on the quantifier, we switch the quantifier and move the negation to the inside. So here's how it would work with these two quantifiers. So we have an existential and then a universal, and then whatever our functional proposition is. Doesn't matter in this particular example. So what I can do is I can switch my quantifier, the first one, and move it to the right, move the negation to the right. So the existential becomes a universal. And then we have this expression. So the negation is moved one step towards the middle, or towards the inside. And I can also use the other De Morgan's law on the A to switch it to an E, the existential, and then finish moving the negation to the inside. So now we have our universal. This universal becomes an existential. And then the negation is now all the way in the inside. Like so. So the way that De Morgan's laws will work with nested quantifiers is that you're going to switch all of the quantifiers. So the E became an A, the A became an E, and then you move the negation all the way to the inside. So on your homework, you could do this all in one step. You don't have to do all of them. Any questions about that? Okay, so let's move on to the next page. Looks like we're going to be finished early today for once. We have one more example to work through with these nested quantifiers and De Morgan's laws. We're going to do a negation here. So I want to find the negation of this here, maybe we'll put it in quotation marks to be clear about what I mean. So the first thing I want to do is translate this expression into words. And then we'll worry about the negation. We have a universal first, and we're talking about pairs of real numbers for a domain of discourse. So we can start by saying for every real number x, and then we get an existential quantifier. So there exists a real number y. And then we have the actual propositional function on the inside that says x times y is less than 1. Okay, is this one true or false? What's the truth value here?
True.
It's true. Good. So if I gave you a real number, let's just pick an example, maybe x equals -1. What would y be? What's one possible choice of y?
0.
0. Good. In fact, the choice of y equals 0 would work for every real number. So you don't have to have a different one for each x. You can actually just pick a single one, y equals 0. And then x times 0 is always going to be equal to 0, which is less than 1. So good choice. It's true. So now that we've thought through the actual proposition, the original one, let's go to the negation. And we'll look at the symbols first. Okay. So we'll put the negation on the outside of our two quantifiers. And then we're going to use the generalized De Morgan's laws that tell us to flip each of the quantifiers. So the first universal becomes an existential, and then the existential becomes a universal quantifier, and then the negation moves all the way to the inside. So if I wanted to write the negation of x times y is greater than 1, but without the negation symbol, how could I do it just using math symbols? Regular math symbols.
Less than or equal to?
Good. So the greater than becomes less than or equal to. Oh, excuse me. I did make a mistake here. We started with a less than. I copied down the wrong one. But we do the same thing. We would switch the direction. So less than becomes greater than or equal to. And we should also think about the translation. So now we're saying there exists a real number x. Such that for all real numbers y, or for every real number y, whichever word you prefer, and then the inequality x times y is greater than or equal to 1. So is this one true or false? What's the truth value?
True.
Okay, so think it through. We started with a true statement, and we put a negation symbol on it. So what should we get?
False.
Right. So we actually don't even have to think through what this means. We change the truth value from what it started as. But I think we probably should think about what it means. So I'm saying that there's a single real number such that for every other real number, if I multiply my single number by that, all the others, I'm always going to get something that's greater than or equal to 1. So can you think of a single real number where this would work for every other number?
1.
So what about 1 times minus 3? Right, so I think you're seeing the trouble now. Good. Zero, someone is saying in the chat. So 0 times your number would always give you 0. And 0 is not greater than or equal to 1. So that won't work either. And you're not going to be able to think of a number where this would work. If you did, math would be totally broken. So don't try. Are there any questions here at the end of class? At the end of the section?
Can you explain on that last one again, like how you got that it was false?
Sure. There's a couple ways. We started with a true statement, and then this was our true statement here. And then I
Okay.
put a negation symbol on the outside.
Okay, but like where it says like where you like down at the truth value, you
Mhm.
had said like there was a way to check and make sure that you were actually right, I
Okay.
guess.
So what this is claiming is that there's a single number, or maybe I'll say it the way that's true. There is no single number that makes this true. For every y. So maybe Luan meant something a little bit different when he said 0. The way that you could confirm that this is definitely false is because no matter which number you pick for your single number x, y could possibly be 0. And then your real number times 0 would always be greater than or would always be less than 1 instead of greater than or equal to 1.
What I'm thinking.
Okay. Yeah.
And because I just think if the proposition on with 2 and then the negation of those on with 4, so I don't have to think at all.
Right. Yeah, that's what I was saying up here. You don't actually have to think about the meaning because we already know it's false. because we put a negation on a true statement.